Okay, thank you. Okay, so I'd like to thank the organizers that this is really nice to be here to give these lectures. So I will be confused. I hope you will be confused, and maybe at the end of this one week session or week and a half, we are a bit more clear about things. Okay, so I'll talk about physical properties of asteroid surfaces, and this is the point of view here is in their interpretation of spectra, basically near-infrared, visible near-infrared spectra. But in order to do that, actually, we will have a long tour, in fact, and I'd like to spend some time in the introduction first. Okay, so the outline, I think I'm going to follow the outline of these 4 lectures that I actually sent last spring. So first, some introduction to asteroid UV-VIS-NIR spectrometry, and I think this might, at least today, be a minor part of the lecture. Then tomorrow, I think we go to novel spectrometric modeling. Next week on Monday, I think we'll have some hands-on application, and I think tomorrow I will specify something for you. If you want to share some wonders of spectrometry, I think I can give you an example and do a kind of a task. This is on a voluntary basis, but I really encourage all to get into that, and I think I'll do that myself also. So, so as a matter of fact. Okay, so finally, I think on Monday, the second lecture, then I think we'll have some use about combining everything that we have, basically spectrometric, polarimetric, photometric observations, to say something about the physical properties of asteroid surfaces, and then today. I think we will start with the tour from polarimetry to photometry, polarimetry and photometry to spectropolarimetry, and then we go to asteroid visual near-infrared spectrometry, and we go into that in terms of the asteroid taxonomy view. So we want to actually strive toward some classification for the millions of objects out there, in fact. And then, as an example of a nice analytical model, I think I will explain the so-called Shkuratov radiative transfer model, which is basically a slab model. Very useful approximate model that you can analytically calculate in the forward direction, and you can analytically invert also the parameters in the backward direction. Quite useful for getting a feeling what the spectra is about, basically. Then, if there's time, I think we'll be, if I have the 1 hour, let's see. There then I'll describe some Monte Carlo radiative transfer for meteorite spectra and come up with some conclusions for today. So basically today, I'm not going to tell much about any new methods. I go back to the existing techniques at the moment and see where we are, and tomorrow we touch upon the situation with the, what is it this? I thought, just a moment. Okay, yes, sorry, I just remembered. Okay, so tomorrow we'll do this in detail, from the point of view of new novel techniques. Okay, so what do we want to do? And this, as a matter of fact, this is the same story for basically whether we talk about photometry, polarimetry, or spectrometry. So basically want to characterize small particles and the particulate media in asteroid surfaces. So we have the loose, unconsolidated layer of dust on the surface. There can be also solid surfaces. You want to characterize that material in terms of first principles, basically. The forward or direct problem then is that you compute from given basic parameters. And what are the basic things? There's like particle size, shape, structure. Basically nowadays you can specify this to nanometers, in a nanometer scale. You can actually say extremely precisely what you put into the model and then compute. Okay. And then you have the optical properties there also for the material. The inverse problem then is that you take the observational data and then try to say retrieve useful information. And what are the basic things here that I definitely we need on this during the way here is that you have the asteroid here, and then we are here, or there's a spacecraft. So this is always necessary to point out. Basically, we have the light source, the asteroid, here's the sun, and this plane here is the scattering plane, then precisely defined by this geometry. And a key angle here is the phase angle. This is the angle between the sun and the Earth as seen from the object. So full moon, as you all know, is at 0 phase angle then. Okay, so what happens now? If you look at the literature concerning spectrometry, for example, you talk about phase angle effects. It's kind of a title for all angular effects that you may imagine to be there. Of course, if I specify that this is not only the asteroid, but it is an element here on the asteroid surface that has a normal vector, I actually introduce 2 more angles immediately to the equation. So there is a surface element, and then we expect to have a scattering response of spectra as a locally disk result from the surface, and that adds more angles. So in disk result cases, we have 3 angles. You can actually replace the phase angle with the azimuthal angle on the surface, and you have angles of incidence and emergence from the surface normal. Then, okay. So that's the plane. That's the phase angle. And then, when we discuss the polarization in a second, we have a system here where we have the perpendicular component. Let's put it this way. And then, just a moment, I think that's correct, in this way. So the degree of linear polarization for incident unpolarized sunlight would be this quantity. That is the classical polarization quantity. That all that comes around here is basically defined like that. So you need to remember the plane of scattering and things like that. Okay, so that was a first introduction. The second introduction is that this really is about the physical properties. So I will not be giving you an evolutionary aspect of the main belt of asteroids, for example, or the Trojans. I would be perhaps tempted to do that because John was explaining the TNOS from that point of view to an extent. But instead, I think I will focus on the spectrometry point of view here. Of course, what comes before the physical properties of asteroids? What do you do first when you actually observe an asteroid, discover an asteroid? There's the orbit. The sequence of analysis is that you derive the orbital elements. You characterize the orbital elements probabilistically. For example, what is the distribution of AEI, capital omega, small omega, mean anomaly M. There's your distribution. Then you refine the orbital elements by carrying out more and more astrometric observations. Once you get into realistic orbits or refined, well-determined orbits, what you can do next is you take a light curve. Of course, this is not as easy, you know, it's observational approach. So depending on whether there is an opportunity to do these observations, it can be more challenging or less challenging. So assume you have a light curve. You can estimate the rotational period of the object. Once you have done that, get an estimate, you collect an extensive set of light curves in which after you get a light curve inversion possibility for actually the spin state in terms of the polar orientation of the asteroid, and then you actually can derive an overall shape model for the object from the light curves. So that's the point where you have utilized maybe the basic dynamics, dynamical modeling plus basic photometric modeling already for the surface to actually derive the shape and spin characteristics. After that is kind of in the sequence you get into the physical characterization of the object itself in more detail. And in that you can do that in various ways. This way is basically the scattering way now that I'm presenting. Okay, so let's see some animations first from Minor Planet Center. And I wonder how well you know these. I've utilized these amazingly many times. So I always show these to students, first year physical sciences students at the University of Helsinki. They are from Minor Planet Center, and I'm surprised how little these are weathered during the years. So what you see, everybody is surprised, the same effect that John was showing earlier, that everything is aligned at the time of the discovery of the TNO groups. So the astronomical bias is very nicely here shown, and nice to explain also to people that in fact this is quite natural due to the discoveries taking place in the 90s then. Okay, so if you come to the middle solar system, so what happens is one can now move to the asteroid region from the Transneptunian or regions, and then you see the clouds of Trojans there, and then the main belt of asteroids and the terrestrial planets here. And then if you are not too claustrophobic, you can have a look at the inner solar system, because this always knocks people out when you look at this simulation where you are actually enclosed in this curtain of asteroids everywhere, and you start feeling bad about things, and then then it is even worse if you go to the actual near-Earth object population. Just a moment, let's enjoy this. Okay, I think done. And then if you ride with the Earth for 1 year, this is in 2007, 2008, with real objects in the proximity of the Earth, and this is what is happening all around us all the time. And the situation is of course much improved. There's much more objects at the moment after the discoveries since 10 years ago. And the red ones are the bad guys coming close. I think this was like 20 lunar distances. You're looking at from the ecliptic, so basically you can have green guys go under or go over, and these are green still, but if you come to 20 lunar distances, that's critical. Okay, and now we have visited, thanks to the Dawn mission, we know I think this is Ceres. We know the largest asteroid, or the dwarf planet, Ceres now. Not much more about that. You can see that, okay, this is patterned with craters, and we have the sequence of asteroids. Vesta is missing from this plot. I can show Vesta maybe tomorrow in another day. You have a sequence of asteroids here and some cometary nuclei also. And this is how the small solar system bodies look like. And then, of course, we have the favorite one from Rosetta mission, the comet Churyumov-Gerasimenko now. It has the nice dusty envelopes there around the very fascinating nucleus, basically. Okay, so these are the objects now. We want to say something about their physical surface properties now. And for that, let's have another history tour, and let's go to look at some really old stuff from starting from the moon, basically. So this is now an observational collection of key phase curve observations, photometry and polarimetry. So we are looking at the visible band photometry or polarimetry, and now the polarization definition is exactly that. And if you look at the photometry of the moon, this is a very featureless curve, except for there is the opposition effect for the moon. And then if you look at the polarimetry of the moon, which is at maximum half moon, you basically have almost 10% polarization here. This is where I never remember which one comes first. When the maturity of the material is of the moon seen is the Mare regions, we have higher polarization. When we have highlands in the dominating, we have lower polarization there. Okay, but the thing here is that there is this curious negative polarization. So this positive is the typical Rayleigh or Fresnel reflection polarization. Close to the backscattering, within 24 degrees, this polarization turns into the plane of scattering and is negative, which is another interesting phenomenon. accompanying typically the opposition effect. So what is causing that, I'm not going to talk about that today too much. I can only tell you that, okay, almost any surface in this room, including your hair, skin, anything that is disordered, complex matter, actually has these phenomena if you would measure them. Why is that so, and what is the reason for that? Let's return to that in a later occasion. Okay, so if you go from the moon, okay, these come from Roussier. They have averaged, Roussier from 1933, averaged by Bowell et al. For Asteroids 2, book Asteroids 2, and then this is from Leo, 1929. There is no model at the moment that would fit, that one would utilize to explain this curve. So there is no theoretical model there. Okay, I think that is rather typical in our planetary science work, basically. There can be, as we saw, I mean, previous talk by John, there was so many observational curves that you could have zillions of theoreticians work on that and it would still not be finished in terms of modeling, I think. So the challenge from the modeling point of view is quite amazing. For asteroids, we have the same kind of phenomena. Of course, the phase angle now is limited by the geometry of the solar system. So within 25 degrees, we have from F, C, G, M, S, E types, and you see the evolution of the opposition effect. And we see the evolution of the negative polarization branch that now you see is an essential part of everything in the polarimetry for asteroids also. Okay, so typically you have a saturation toward the dark end and you have saturation toward the bright end of objects, and the most pronounced polarization is for G and C types here, negative polarization minus 2% maybe even. Okay, then you may have some fine additional effects. This is not guaranteed yet, but there may be some features really at very small phase angles. We will need more observational evidence there, because I think it is interesting, but so far nobody else but Rosenbus et al. Have actually obtained this kind of data, that there would possibly be another negative polarization peak there. This is an interesting possibility. Okay, I can continue. You can go to Saturn's rings. This is old stuff from here. This is from 1870s from Seliger and Müller, and this is the oldest, I think, measured opposition effect thing when Seliger was assigning the brightening of the Saturnian system to the ring system, and then we see the opposition effect there, which is substantial here, and then the polarimetry again is negative from Leo, again 1920s, very old material. Very fresh material next. This is the Transneptunian objects now. So we have polarimetric data for the Transneptunian objects, and we can see that the large TNOs that are capable of maintaining their volatiles typically have lower polarization values here, and then the smaller guys actually have more substantial negative polarization. And look at the phase angle now. This is within 2 degrees from the opposition. So the nice thing about TNOs, okay, nice or challenging thing, is that you are always looking at TNOs at almost exact backscattering. So that is the most challenging place to actually model the scattered signal from them, basically. There can be surprises because of various phenomena. Okay, I say a few words in a soon. So you can continue, and this combines now, this links the photometric and polarimetric history now to Spectra. And this is from Belskaya et al. 2009, and we can see the phase angle for these given asteroids, and then the polarization degree at that phase angle across the wavelength. And one can see trends. These are now already reliable trends in the spectra. So now we have polarization spectra. So we were not actually really fitting or providing a model for the polarization for a single wavelength. Now we have a wavelength-dependent polarization dependence here. Okay, and now we have the spectrum. And if you still go to newer ones, we have basically substantially very interesting work from Paniulo et al. 2015, which is now what we would call high-resolution spectropolarimetry. So now we have completely new stuff, very high-resolution spectra, and what you have, an interesting thing is that this curve and the blue curve, if you look at this and concentrate on the pairs of reflectance and polarization, you see that they are not all the same. I mean, the qualitative behavior is, I think that the blue one, this light blue one goes down, it goes up. I think I have one example where maybe this blue one, then another blue one. You do not have the same qualitative behavior when these are all fixed at the same position at about 500 nanometers here. So what is explaining this? What is that telling us? The authors here say that we are just about to experience something that was experienced when the spectrometry, typical intensity spectrometry, was introduced some years ago or tens of years ago. Now we have a possibility to do polarimetric spectra, and we do not have a clue what to do, how to interpret that now. So this is why modeling definitely is also called for all of these, both polarimetric and spectra, or spectropolarimetry and the normal spectrometry. Okay, so this gives us the bridge to this asteroid visual near-infrared spectrometry of today, basically. Well, this is just the cumulative discoveries, annual discoveries of asteroids, so what the numbers that we are dealing with in the interpretation. At the moment, basically, we must have well over 700,000. Back in 2015, the number was this 700,000 known asteroids. It's way beyond that now, and you see that this is hitting through the roof here. So I don't know whether 1/1,000,000th of asteroid is. It's around the corner, if not yet there. I mean, not many months or years needed to reach 1,000,000 asteroids, known asteroids. And about the characterization, one interesting statistic is the WISE space mission characterization of about 100,000 asteroid physical properties. So one can argue that there's been a lot of improvement from that point of view. But still, I think the discovery rate is so heavily going up that it is extremely difficult to keep up with physical characterization. Anyway, that's interesting. The interesting thing in asteroid is the large numbers, definitely. You know, that to me is an intriguing thing. Okay, so when you look at the spectra of these objects, so what do you see? Well, I'll show you the spectra just here in the taxonomical view. Pas de meo taxonomiki. Okay, I see. I misspelled some names. Sorry about that. Okay, pas de meo taxonomiki. This is correct. So we have the SCX complexes. So 3 of these complexes, and then you can judge how different do you think the curves are from each other. Okay, I just question this now. How fragile is this taxonomy? I mean, if you look at the okay, I see that you can say something about there are some certain definite differences, but what about the how solid, how consolidated is this taxonomy? Okay, let's see where we come. And this is based on observations. So you do spectroscopic observations from the visible to near infrared, and you run this through a principal component analysis with some typical constraints, and then you get this kind of kind of classification. And I think this is the best we can do, basically, based on the observations. This is our view. If you try to make some order, introduce some order into the data and classify everything. Okay, so then this is, you're not expected to actually read this. Then we have the different 3 taxonomies or 4 taxonomies, starting from Tholen, Gaffey, Buss de Meo, which is, and then you see the different curves here. Maybe the Tholen one is okay, we'll see that. You look at the curves only here. So S, that was the Tholen. S only is now basically in Buss de Meo. When we have included the near-infrared, it has 5 classes, or what would they be, types, maybe, sorry. This is the C complex, was 4 members there. Here we have 6. This was a single EMP. Here we have 4. Then we have 6 here, and then a plethora of curves here. Other end members, outliers. Okay. And let's look at that more carefully now. Let's start from the S complex now. So what do we, what is at the same time is an introduction to what we expect is in the regoliths of asteroids, basically. So S complex, there's 7 of these in Gaffey. This is like a mineralogically oriented classification. There's 6 here with Buss, and then we have the 5 here now. So Tholen defined only S. Gaffey had 7 classes, and this was the band 1 center. I think I'll introduce those in due course. Band 2, band 1 area ratio, so band 1 is basically here, band 2 here, and then this separates in his taxonomy olivine orthopyroxene ratio is the basic thing. The Buss has this kind of particular drop in 0.9 micrometers, and you see this is the typical thing with spectra that one starts to think about. Really minute changes in the spectra, some features that are particular for certain minerals there. Buss de Meo, there's the 1-2 micron feature in near infrared, and then there was something removed and added. So what are the relevant minerals? And these are the basic most important minerals, olivine and pyroxene. And from the meteorite part, you see pallasites, R-chondrites, brachynites, ordinary chondrite-like materials, primitive achondrites, basaltic achondrites. It's a long story, and if you go to meteorites that have been actually characterized in the laboratory, it becomes extremely challenging actually to follow the classification and analysis of the materials there. Okay, so if you go to the C complex, this was originally in Tholen taxonomy DCFG, now it is like that, and if you look at the minerals, opaques, carbon, phyllosilicates, there is olivine pyroxene there, and then carbonaceous chondrites in meteorites would be the counterpart, and then impact melts, heads, these were the Vesta meteorites then. If you go to X complex, there was EMP here, there's X, XC, XE, A, and now we're talking about again opaques, carbon, pyroxene, enstatite, oldamite. And then there is MP, M. Do we know anything about M? It's metal. Originally it was metallic, but we don't really know how much metals there are. E, enstatites. They showed very interesting photometric and polarimetric behavior just a moment ago. Okay, so now the other end members, outliers, here and here in the newest taxonomy, TDQORVAKL. And what do we have here? And it's a list of minerals and materials, a long list of minerals and materials. Okay, so this is kind of the playing ground we have here. And if you go to the main belt or across the, let's go across the main belt to the Trojans. Basically, there is this nice plot from Karri that actually gives us in kilograms the amount of material in each section of the main belt, basically. So you can go to the inner Hungarias in the size range, and you have a size dependence on this composition here, expected composition. Then there are places where there is no data. Okay. But in the overall picture is that the C-types are actually more pronounced towards the outer main belt, and the S-types are more pronounced in the inner main belt. And then it is also a size-dependent thing, so depending on which size range you are looking, the behavior is different, basically. So that's kind of the section through the asteroid belt as it is right now. Okay. So now let's move ahead and look at some more detailed spectral dependencies. Okay, so first of all, there is a well-known phenomenon on the spectra that there is the so-called phase reddening. So if you change the phase angle, this was the phase angle alpha here, you increase it from 13 degrees to 30, 60, 90, 120 degrees. There is an example measurement here, absolute reflectance, and if you follow the maxima, their behavior, this is at about 0.18 here, and it is reduced down to 0.09. This is a factor of 2. If you look at this maximum, it's maybe not that much more different, a bit less than a factor of 2. If you look at the paths towards the ultraviolet here, this factor is enormous actually there. You have reduced the signal enormously from the original signal. That means that you basically tilt the spectrum towards red, and so you have a phase reddening as a function of phase angle there. So the spectra should in somehow always be corrected for this phase reddening before they are actually comparable to one another. And that's why in many cases, I don't remember exactly the details now concerning the taxonomy, you basically take away the slope when you classify the system. So if there is an overall slope, you remove that to remove the phase angle effect. Okay, but that's the best thing one can do basically, quickly I would say. Okay. So then, there I show you the next challenging thing, which is how you would actually classify a spectrum, basically. I think this is like a flow chart, what to do when you obtain a spectrum. I think it's amazing that you calculate ratios, then you plot, and then there are certain ifs here. There is actually no what if none of these are true. Okay, let's see if the asteroid plots in the certain region, and in certain region, so you do various things. And I think that there is an enormous amount of wisdom from experience from people with laboratory measurements and observations that actually they devise this kind of a tree of how to actually interpret the spectra. So that is not something that can come up very quickly in a moment. It is with experience on how the spectra actually evolve. And then that recipe, I think, is a good recipe then to introduce or to characterize spectra. Okay, so let's move on now. Maybe forget about the population view for a moment, and let's look at the actual modeling or processing of spectrum. So one very popular model is the so-called modified Gaussian model, or MGM, and this is basically I would just say that this, maybe it will insult somebody, but it is a fitting tool basically. So you have Gaussians that you fit to the, and you can maybe justify the shape of the Gaussian line profiles from some physics point of view, but nevertheless it is largely a tool that is an empirical tool to express the spectrum as well as you can possibly can. So in my view, this is similar to actually fitting a spline through this system, for example, or any interpolation thing here. With the Gaussian, with the MGM, nevertheless, you can position the minima and maxima in a useful way for asteroids spectra, for example, for pyroxene and olivine. So that makes it maybe very useful precisely for asteroid purposes. Okay, so what you end up? Okay, let me see. So that is one example of really fitting a spectrum as precisely as possible. And you see there is maybe there is some bias somewhere, but not much nevertheless. So just a moment. Actually, I don't really. What do we have here? We have actually the meteorite connection here. So how do the asteroid spectra for Itokawa and Eros actually compare to certain meteorite classes H, L, LL? And you can see that there was actually a question about Itokawa, whether it would be, was it here or here? And I think at the end it was predicted by Pinsel basically that it was be on LL, so low iron meteorite counterpart asteroid, and it is sitting there. Somebody was hypothesizing L in another way, and then for Eros we have here an L-type meteorites being the counterparts. Okay, so let's move ahead with the physical modeling now. So what can we do to improve the situation here? So this is like fixed fitting tool, and by the way, we do have equivalent fitting tools also in Helsinki, and they are online. Basically, you can fit any spectrum with a spline tool as well as you possibly can, and so on. So there are various other ways not mentioned here. I'll dig them up for tomorrow then if there's time. Okay, so let's look at the modeling part now. So this model is something that one would typically take as a first approximation, because when you specify that you have this kind of a normal incidence to a structured slab of material, you can do a lot of analytical calculation immediately. So basically you can replace the realistic system here with the system that is simplified, but which has the same physical parameters here. In here, I would perhaps, this is from Shkuratov's work, I would add maybe some internal inhomogeneities here. They are not visible in the system that is described. So basically you have like geometric optics type reflections, refractions in the system here. In reality, these particles are highly inhomogeneous. You have a diffuse scattering inside. You may have surface roughness that is also diffusely scattering, and all that would need to be taken into account. But as a useful first order analytical model, you can replace this system with a slab where you have basically these reflections. So first you go down, you reflect back, go like this. There's an example path, so you come up from the fourth or third slab, you actually escape back. And when you do that, that's an analytical result, and Yuri Shkuratov actually did that all analytically, and there is an analytical formula for this forward problem. everything is spelled out. These are the slab reflection and refraction coefficients that you can actually relate into first principle parameters like refractive index, basically. So what you have is the tie between the spectrum and the refractive index. That's useful. There is here also the optical thickness tau, but when you go to a semi-infinite system like an asteroid surface, you can just take the tau to a limit of infinity and delete those parts from the system. Okay, so that gives us a possibility to compute what Yuri Shkuratov calls an albedo of a particulate system. Okay, this would be our maybe reflectance in some respect. Okay, so I would not like to use the albedo word, but nevertheless, this is how the original article was utilized, and here is the result. And you plug in everything, and you have the forward problem. But the nice thing, I don't go into the parameters here, except that in the inverse problem, this now is the imaginary part of the refractive index. I think, if I recall correctly, I think he must assume that basically there is a real part of the refractive index assumed or fixed somewhere, and then he can actually then come up with the actual absorption related imaginary part of the refractive index. So this model is an example of a model where everything is tied down to the first principles of physics. That is basically the Maxwell equations. So you are in the Maxwell equation range, you specify parameters that you would specify for an exact computation starting from the Maxwell equations, basically. Okay, so why did I put that here? This is, I think, I was mentioning earlier this exercise or some project work. I think if you like to get involved in that work, I would actually suggest that you actually get this article. You can get it from me, and you just program this analytical model for your purposes. If you don't have it yet, it is not only for asteroids. You can do any spectra in the visible near-infrared range if you just plug in the parameters as they are. So Yuri was utilizing this for the lunar spectrometry, so we could utilize it for the asteroid spectrometry. And it is particularly useful as a tool for the inverse problem, because with certain assumptions, you retrieve a physical parameter from there as a function of wavelength. So you basically repeat this analysis for each wavelength, and you run through the spectrum, and you get the dependence on refractive index on the wavelength, which is very interesting, by the way. And it turns out that, in my viewpoint, this is one of the biggest obstacles actually in going into quantitative modeling of spectra, that we don't really have the properties, the optical properties of materials. If you go to the web and you try to search for typical pyroxene optical constants, there's nothing. There is only a work, there is work from a couple of years ago, I'm just missing the reference now, where they did exactly the same thing. That you take this kind of modeling and you make the measurement and you apply the modeling and retrieve the optical constants and claim that this is the refractive index. This is the best that can be done in many cases. You would think that this is a thing that the physicist would have solved a long time ago, but no. This is not existing as a tool anywhere. So it turns out that for olivine, for example, you have in the nice database in Jena, you have a optical constant through the visible near-infrared range, but for orthopyroxene or pyroxene, I don't think you have. You can correct me if I'm wrong, but that looks like the situation. So in order to utilize models like the radiative transfer model here, so one should first actually develop a library of these optical constants for relevant materials, and that's kind of missing now. So tomorrow, when I discuss this problem a bit more in more detail, I'm going to tell you that I'm telling it now, in fact, that there are some reasons to believe that we can work toward getting this kind of basic data for basic materials from the measurements that we typically do with spectrometers in the laboratory. So let's see. It means that we can improve the modeling that Shkuratov et al. Are giving here to such a precision that we can claim truly that it actually describes the particle optical constants as a function of wavelength. And we can combine this with measurements on. We can combine both single particle measurements and with particulate media measurements, and then we are getting there to the goal. Okay, but there's a lot of work, as you can see. So this only is the background enabling actually quantitative interpretation of spectra. It's not yet the interpretation, but it is the tools needed to interpret. Okay, and there's a Shkuratov model fit to put to the Itokawa spectrum, and it's quite nice. Okay, except here there was a particular reason why it is not working here, and maybe it had to do with the optical constant precisely, so we should not claim the model for this discrepancy so much. Okay, so time is at 1 o'clock. Do I? Okay, good. Okay, so the final topic basically is the following now. So let's have a taste of Monte Carlo radiative transfer here. And this is a story that basically is from Hanna Pentikäinen et al. From 2014. And now we have their spectrometric capability in Helsinki to measure actually with several instruments. 2 instruments basically. There is a spectrogoniometer at the Finnish Geospatial Research Institute, running from the ultraviolet to 2.5 microns goniometric facility. So you can have a spectra with these precisely the angular dependence there. And we have at the University of Helsinki, we have an integrating sphere visible near-infrared spectrometer to obtain a spectrum within the integrating sphere. Okay, so the key thing is that we wanted to start this modeling work and improve the existing models and do this in a way where basically we would take existing single particle properties from measurements by Olga Munoz and her colleagues in Granada, and this is, for example, an example of that, of the feldspar measurements. These are atmospherically relevant materials. Don't worry about that. We are going to do this with olivine. 10 micrometer bar is here, and 10 micrometer bar is here. So there's a size distribution of feldspar particles actually run through a measurement volume, and you can characterize the ensemble average single particle properties at 2 wavelengths from this laboratory work. Very nice. And what you have additionally is the precise size distribution of these materials. This is in microns. This is for the olivine now. The picture was for feldspar, but these are the olivine S and XL size distributions that we actually plugged into the Monte Carlo radiative transfer model. Okay, this is a bit confusing because I did not have time to replace some of my figures. So I step from feldspar to olivine, and then to show example measurements in the Granada laboratory, I go back to feldspar to show the typical scattering matrix measurements that they do. And don't worry, they look rather similar for the olivine particles. Okay, so what does this measurement include? It includes the theory. I see I did a very mini theory section in the corner here. So you see that we have incident Stokes vector here, and we have the scattered Stokes vector here, and you could think of this as being in the laboratory, that there would be a laser source here and the particles streamed through this volume, and then the measurement would be done here, and this is a scattering angle. So scattering angle, which I did not explain earlier, is the pi minus the phase angle. So forward scattering would be there, and the pi minus alpha gives us the scattering angle. So alpha 0 is backscattering is at 180 degrees now. So what you have here is the intensity distribution for the scattered light as a function of scattering angle for incident unpolarized light. So if you would have unpolarized light in the incident Qi, Ui, Vi 0, you would actually have this dependence for the intensity that is scattered, the Is here. And then changing the polarization, this is basically a modulator system, so it allows for measurement of the polarization characteristics in a quite smart way. So this is the polarization, exactly this, corresponding now to the single particles. And what you have here is an interesting thing, another negative polarization branch now for the single small particles in the micron range, basically. So this is highly interesting. So we see the same thing for the moon, for the asteroids, and we see that in the laboratory for this size distribution of irregular small particles. Then this is a depolarization measure, this P22. For spherical particles, this would be unity, no depolarization. For the realistic non-spherical particles, there is substantial depolarization. And these are related to, again, linear polarization, and then finally to circular polarization characteristics. The most important and interesting things for us is this one, and then the polarization one. And the example that I'm going to show now has to do only with the intensity. So let's take the laboratory intensity distribution for scattered light and plug this into the Monte Carlo routine, and then make an assumption, for example, that okay, all through the range of wavelengths you have the same phase function, and then what do we if we make that assumption, what can we say about the single scattering albedo in the medium? What would be the single scattering albedo with this phase function that would produce the spectra that we are measuring? So it's a different setting from the Shkuratov model that has the parameters. This one does not yet go into actually telling us what the parameters, what the optical constants are. It is actually telling what the single scattering albedo of those particles should be with that phase function to produce the spectra. Okay, so this is the example for 442 nanometers for feldspar, and this is for 633, and then we go to first to the measurements that were done for the spectra. So this is just an introduction to remind us that there is the olivine spectrum, and there's the pyroxene spectrum, and then we have typically the carbon, which is quite flat here, and this should be rather absolute here, I think. So these kinds of monsters we typically have, and the measurements that Pentikainen et al. Did were for these meteorite samples, and here we then took some olivine samples. I don't actually, let's see if it comes up, but it's some of these cases that we considered the olivine was a good match, and then what we modeled the phase function for single scattering with the 3 Henny-Greenstein, so and kind of just a fitting tool, just to express that with the 3 Henny-Greensteins, and then we have the parameters here and the goodness of fit for the different olivine samples. So with 5% RMS, you can fit the entire curve here, this kind of curve with the Henny-Greensteins, and put it into the Monte Carlo code. This was in fact Hanna Pentikainen's own code, actually. She wrote the code and did all the computations with that code for the spectra. Okay, so more of these. And before the interpretation, the single scattering albedo, I just point out that it is an intriguing thing to see measurements of spectra like this, which look like you have the same spectrum, but you have to really bend enormously to match them, and they're still related definitely. So other measurement spectra, another one set. Okay, and then finally I think we have the single scattering albedos, and with what is actually the most intriguing thing here is that if you have utilized models like the Hapke model, for example, you typically have very low single scattering albedos. But if you plug in these measurements into the codes, you actually are dealing with single scattering albedos in the range 0.8 to 0.9 for this case here. What do we have here? We have 0.8, 0.75, 0.7, 0.8, and this is for different L and H chondrite spectra: A, B, Bushhoff, Citado, Sevrukovo, Jilin, Suslovo, Meno. And all through this, basically the numbers are high. So they are not in the range of 0.1 or 0.2. These are high numbers in order to produce in absolute terms the spectra. And this is big. Why is that? That is because of this one peak here. The realistic phase functions are highly forward scattered. So in order to have a backscattering that you typically measure, you have to introduce a higher albedo so that the multiple scattering actually returns the signal from the sample, and that is the key thing in this game. Nevertheless, I would say that one has to be careful not to draw too hasty conclusions about the Hapke modeling in comparison to this kind of Monte Carlo modeling. It is not obvious that the models actually involve the same parameters. You know, we can discuss different things. These are like the used with the like a fundamental scatterer that is in the micron scale, submicron scale. Hapke modeling may rather involve larger chunks, like entities of 50 microns, and that's a different story than to model that. Okay, I'm almost done. This is so difficult that I'm not saying anything about. We did some PCA also with the meteorite spectra measured, and then to today's conclusions I'll draw here. So basically all this in a conclusion here, and the conclusion also in Asteroids 4 in the leading chapters, the first chapters actually concerning what should be done in the future before Asteroids 5 comes around in 10 plus years, hopefully, is to go into the first principles and understand the relation of first principles optical constants to the spectra, and that's the only way one can do that. And here, although everything looks very confusing and chaotic, the key thing is that the basic problem is very well defined. The challenge is only in how to compute a spectrum for a specified sample material or model or structure or of certain composition. This is very well defined. The inverse problem is difficult. Okay, so now we can be always we can do the forward problem. We can do this forward problem with the viewing geometry, particle size, shape, structure, and composition also. Then there is an interesting question. So what do we learn from astronomical observations and laboratory measurements? Are we measuring the same things? Meteorites in our possession are actually thought to be coming from only 150 different parent bodies. Only 150. Think about that. It's a very tiny part of the actual population of asteroids. That may mean, who knows, that it's not a representative set of material from the solar system, small bodies in that sense. So prospects, one can argue, can we ever do this routinely from the first principles? Imagine that we could possibly measure all the materials in the laboratory and do the actual optical constants for all reasonable materials at any reasonable temperature. We actually could have a library that would allow us to determine basically the everything from the first principles. And then how solid or fragile is our understanding of asteroid surface properties based on, for example, the spectra? We will see. Let's develop the story further tomorrow then. Okay, thank you.
Questions?
Hi. I haven't heard you speak about something which I particularly enjoy.
What did I miss? Yes.
Well, I'm not going into the app Shkuratov debate, but regarding the space weathering.
Yeah, that's a good point.
Because you haven't talked about it.
I'll talk about that tomorrow. Yeah,
okay.
I have some
the details because well, when you're doing direct comparison, I know it's really difficult to evaluate what might be the change in the surface of the asteroid.
Yeah.
But even we need to take it into account up to a certain point.
Yes. Okay. I can comment that much that basically the space weathering, if you think about the introduction of nanophase iron in the particles, well, that happens to be in the size domain where we can really very nicely utilize exact computational techniques to actually characterize what does that nanophase iron actually do for the scatterers, what happens there. So that's maybe basically the most appealing example to assess basically.
But
first.
Then a follow-up is actually regarding laboratory measurements. The problem is that usually when we do spectroscopical analysis, we do also irradiation, but using another apparatus. You usually don't have you're just like irradiating your sample, taking it out of the irradiation chamber, and then doing the spectroscopical measurement, which is a problem. And also usually when you have your apparatus, you also have a fixed or very bounded illumination condition. So that's also maybe a problem that our generation needs to work together.
You are right. This reminds me that I did not want to mention that, but for example, what we have in Helsinki, the integrating sphere spectrometer. Okay, so imagine that you actually shine light into the integrating sphere and to the sample, and then you get the spectrum by measuring with the detector within the integrating sphere. Okay, in order to compare that to a spectroconiometric measurement, you would need to model the interaction with the integrating sphere itself. And what does that signal actually mean? So you would have to model the entire system, the measurement system, before you can actually compare to the spectroconiometric measurement. So the spectroconiometric measurement in that respect is more fundamental, I would say. So this is actually one example that I proposed for one student at some time. I remember, was it maybe Julia? Yeah. We need to model the entire integrating sphere before we understand what the spectrum actually means. So we cannot utilize that spectrum for optical constants characterization before we model it, in fact. And it's the same story. So if you mention that things are done like many commercial spectrometers are exactly like that. So it's like a black box, basically. You do not know how to go from the spectrum to the optical constants with that machine. Yeah, it's a challenge. I agree.
More questions? No?
It's lunchtime.
So, we can go for lunch. Karri? We come back at 3? 3?
Yes, evening sessions start at 3 at a bit. And for lunch, you have several options. I think it's not raining now, so what I would recommend is that you get outside and basically you can see, you can go walking up, but you can walking down and you will know that it's a bit tough to get there. But then you can get the tram, okay? You have the tram stop and have a lot of options there. Okay, small restaurants, cafeterias, whatever. You don't have a sandwich or not, or lunch. You have 2 hours. So you have plenty of time to come back here. And to get
1:45.
coffee.
1:45.
Okay, it's enough. You can also have lunch here. We have